Hello, welcome to 13 Universal A-Level CAE Biology. We are doing Advanced Practical Skills 2024 Exam Checker, May-June Series 2. Okay, so if you're writing this exam, May-June Series 2, you're writing May-June 3-1. This is actually 3-1, which is on the 9th of May. So come with us. Let's go through these questions that are likely to come out in the exam, and this is schedule. So let's go to the first one, guys. This is microscopy. When plant cells are placed into sodium chloride solution, osmosis occurs and water will enter or leave the vacuole. Some cells become plasmolized. A cell is described as plasmolized when the cell surface membrane detaches from the cell wall. Okay, when cell wall and cell membrane are fighting, that's plasmolysis. They separate. We call it divorce. A divorce. They've been married. Now at this point, they cannot solve this problem, so they detach membrane. Cell membrane detaches from cell wall. That's plasmolysis. You will investigate. Always pay attention to what you're investigating. The effect of different concentration of sodium chloride solution on onion tissue. All right. So which of them is the independent variable? Which of them is the independent variable? Okay, which of them? Of course, effect of independent variable on dependent, so different concentrations. All right, let's see how different concentrations of sodium chloride affect onion tissue. Okay, let's go to the next paragraph. You will need to prepare. Now this is a practical exam. We may not be able to do it, but I'm guiding you through on how to deal with practical exams here. Of course, the first thing is you have to read instructions and the procedure. Okay, adhere to instruction and procedure. But as you are reading, you must be looking at what is it that is my independent variable, what is my dependent variable, what is the independent. That's different concentrations of sodium chloride. So that's what we are going to be changing now. Solutions, the effect of this concentration of sodium chloride solution on onion tissue. So what effect does it have? Does it make them plasmolize or not? All right, let's go. Prepare different concentrations of sodium chloride solutions using proportional dilution, 4.0%. All right, sodium chloride solution, that is a stock. So observe and record the effect of adding these concentrations of sodium chloride solution to the onion. You are provided with the materials. Okay, so we know the independent variable, we also know the dependent. Okay, that's what we're measuring. Okay, let's look at what. So once you are in the lab during the exam, check this table gives an idea. Look on your bench and check all of these items labeled X. All right, look inside. The content should be 2 pieces of onion tissue in distilled water. So this is in distilled water, X. All right, it's not hazardous. Okay, no particular volume. Now check S, which is 4.0% sodium chloride, no hazardous. All of this is distilled water. Okay, so it is recommended that you wear suitable eye protection because onion can stimulate tears production from your eyes. You will need to prepare different concentrations of sodium chloride solution S. So this is different concentration. All right, S we're going to dilute 4%. All right, using proportional dilution. You will need to prepare 10 cm³ of each concentration. That means that this is final concentration. Sorry, final volume. The volume of water and the stock. The stock is 4% here. Come on, let's do it. AI, hope you're ready to solve this question. 1.2, table 1.2 shows how to make up 2 of the concentrations of S you will use. Decide which 3 other concentrations of S you will use. Complete table 1.2 for the other concentrations you will use. Now I want you to complete this. Pause this video and try to complete it. Okay? Remember that 4% is our stock solution, which is C1. Okay? And then C1 is 4%. That's what we're diluting. You know that. Okay? And you know that our V2 is a final volume, which they have told us. Okay, 10 cm³. And if you look at the table, guys, you'll find out that that is 10 because V2 is volume of stock plus volume of water. When you add 2 of them, 10 plus 0 is 10. Therefore, our V2 is what? Our V2, of course, we've said that V1, which is volume of stock, plus what? Volume of water. Okay, volume of water there. So you can see that, yeah, so see that, yeah. So now, if I want to get the first view, and of course, this is going to be because we're looking at different concentration and serial dilution from 4 to 0. What are the concentrations? So the range is 4 to 0. So I need to produce 3 other concentrations that have same intervals. Okay? So from 4 to 3, the interval is 1. 3 to 2, interval is 1. 2 to 1, interval is 1, and 1 to the interval is 1, 2. All right, so if I am going to prepare a solution, all right, of 4, using 4 to make 3, okay, 4 is my stock. So this 3% here, I'll need to calculate V1, okay? My V1 is very important. So V1 is what I'm looking, and then from there I can get my volume of water, the water I'm adding. The volume, the amount of water I'm adding. So my V1, of course, you know this, that C1 V1, okay, is equal to what? C2. If you have been watching our videos, you'll be conversant with it. This is dilution formula. Okay, so V1 is the volume of stock that I want to dilute. All right, what will it be? It will be what? C2 V2. You know that. C2 V2, okay, that's V2 all over C1, okay. C2, if I'm moving from 4 to 3, 4 is V1, sorry, C1, 3 is C2, so that will be 3 times V2 is 10, final volume, all over 4, okay. Yep, so if you check, 4 is here, so 2 goes here, that's 5, you know how it goes. 2 into 4 is 2, okay. So 3 times 5 is 15. 15 divided by 2 is what? 15 by 2 will give us 7.5. So V1 is 7.5 if I'm diluting to produce 3%. So sorry, that's 7.5, not 7.3, okay. So here is going to be 7.5, guys. Yes, 7.5. And don't forget, how much of water will I add to 7.5 to make it 10? I'm taking 7.5 cm cube from 4 to this. So how much of water will I add to make 10? If V2 is 10, V1 is 7.5. So V of water will be V2 minus V1. So 10 minus 7.5, all right, is my volume of water, which is 2.5, okay. So 2.5 here, okay, very important. All right, so if I want to get for 2, I just change my C2. My C2 will be 2, so it will be 2 times, which is final, this thing I'm moving, right, I'm moving from, remember that I'm moving from 4 to this to produce 2, adding water. So it's going to be 2 times 10 all over 4, okay. That's 20 divided by 2 times 10 is 20 divided by 4 is 5. So my V1 is 5. So the volume of water I'll add will be 5, so that everything becomes 10, okay. So if I check, you see that there's a trend here, all right. There's a decrease in, all right, decrease by 2.5, okay. So 5 minus 2.5, I don't have to calculate it again, now I know the trend. So the next one will be 2.5, because I know that they are decreasing by 2.5. So that's the beauty of proportional dilution. So this will be 7.5, because 10 minus 2.5 gives me 7.5 of water that I'll be adding, okay. So we're done with this table, okay. All right, so let's see what the mass scheme says. So the mass scheme says clearly three concentrations given between 4 and 0. We have given it 3, 2 between 4 and 0. Correct corresponding volume of water. And yes, so these are the volumes of water. Okay, W in line with the volume of stock solution. Okay, so let's go to the next. That's 2 marks, guys. Yeah, so remember, you are in exam hall. This is practical exam. You must follow the instructions. You must follow the procedure. Okay, now carry out steps 1 to step 14. Prepare the concentrations of sodium chloride solution in table. We have done that in the beakers provided. Put one clean and dry microscope slide on a paper towel. Put a few drops of W onto this microscope slide. Remove one piece of onion tissue from beaker X. Peel off the inner epidermis as shown in Fig 2.1.1. So this is Fig 1.1. Okay. Yeah. So you see how you are peeling it off. So using this, okay, to peel off the inner layer, this instrument, okay. Yeah. Then to pull it off, you'll be given this, and then, all right. So this is a piece of epidermis. You put it, all right, on the microscope slide. The epidermis, this epidermis you have peeled off, put it on the microscope slide, and then cover it with W, which is water, okay, or any of the concentration. Cover it there, and then put the cover slip on it, all right, because we're following the instruction. Put a few drops of W, and then remove one piece of onion, peel off. All right, what's the next thing? Yeah, cut off a piece of the inner epidermis so that it will fit under the cover slip. Put any remaining epidermis to the label for waste. So put it here. Put the epidermis into water on the microscopes as shown in Fig 1.2. If the epidermis is folded, you may need to add more drops of W so that it floats. So if it's folded, so follow instruction, add more water so that it will, all right, uncoil. It is important to stop the epidermis from drying out. Very important. Put a cover slip over the piece of epidermis on the microscope slide. Use a paper towel to remove any excess W that is outside the cover slip. Observe the epidermis using low power lens of microscope. So low power, not objective. You may need to reduce the amount of light. Yeah, please, when you are doing this experiment, reduce the amount of light because there's no staining. All right, we're not using staining. So if you use high light intensity, it may actually affect, all right, your visibility of what you see, your specimen on the microscope. Okay, so that's why you have to follow this instruction. So let's look at the next one. Now they say you will need to observe and record the effect of adding W and the different concentrations of sodium chloride solutions on the onion tissue. You will do this by counting. See how we're going to measure the effect. How we're going to measure the effect of water and other sodium ion concentrations on tissue of this onion, right? It just, see, they have given us the way. So you have to be observing your independent variable. How do we measure independent variable? It's just by counting the number of plasmolite cells within a sample of cells. Okay, decide the total number of cells in your sample for W. State the total number of cells in your sample. So guys, when you're working on this, remember that in your microscope there's always what we call microscopic field of view. That's the circle of light you see. So this circle of light, all right, you see using your microscope, you see the cells here, you count the number of cells, right? Once you put W, they say decide the total number of cells in your sample. So if you look at the W, you can do estimate. If you can't count all the cells because we're using times 10, you can decide to, of course, divide it into a quadrant. Yeah, a quadrant to make it easy. So you count one quadrant that you can see very well. Any of them, they can see the cells very well. Then multiply by 4. That'll give you the total cells. Okay? Let's state the total number of cells in your sample. That gives you the total number of cells. You record it here. All right? Okay, so see, state according to this practical at least 20 as number of cells based on what you're saying at times 10. Okay, count the number of plasmolized cells observed in your sample for W. Record your result in AII. All right, so you're going to record the result. Take the microscope, slide off the microscope, and remove this cover slip. Just follow it step by step. Now you remove it. Use a paper towel to remove water from around the epidermis. Remove the water, and then now it's no longer what you're going to add. You now put a few drops of the lowest concentration. Lowest concentration. Go back to the video. The lowest concentration we have is 1%. Remember, we diluted 4% to get 3%, 2%, and 1%. Okay, so you now put few drops of the lowest concentration you prepared in steps 1 onto the epidermis. Repeat step 7 to step 8 using the lowest concentration, all right, instead of W. Repeat step 12 to step 13 using the remaining concentration, all right. The 4% sodium chloride solution is used last, so that's the last one. So the idea is start from the lowest concentration to the highest. Okay, so follow the instruction. So let's see the first question. Record your result in an appropriate table. Guys, I want you to draw a table and show me, pause the video, draw a table and show me what should be on that table. Remember, like I told you from the beginning, as you follow this, you must be able to identify your independent variable. What are you changing at your dependent variable? What are you measuring? Okay, so my table should, first of all, you must notice that you must draw an enclosed table. Enclosed table. Yeah, enclosed table. So draw enclosed table. Don't draw table like a market man or market woman. Okay, so the table must be enclosed and it must have a heading. Okay, yeah, sorry, must close well. So this is a heading. Yeah, okay, so you have column. The first column there is for independent variable, which is right concentration, or there's mark for that, concentration. I'll just put conc there, right? Conc means concentration, right? But in exam, write it fully. Concentration of S. Yeah, of S. Now, but remember, this concentration has units. So you put the unit. Unit is in what? In percentage, okay? And then this is my independent variable, this part, this is number of plasmolized cells, okay? Number of plasmolized cells. So number of plasmolized cells. So in the microscope, once you mount the slide on the microscope for each of them of plasma, you start counting plasmolized cells. So I'll put PLZ, plasmolized cells, but you write it in full. Okay, I'm just writing it, all right, but in exam you're meant to write it in full. Okay, so now you must produce cells. Okay, all right, for each of the value we have about 4 values or thereabout, starting from W, which is 0, that's distilled water. You have 0 concentration of sodium chloride, so that would be like 6 or thereabout. So yeah, this is 0. The table should start from low concentration. The next lower is 1, we have 2, the next is 3, the highest is 4. Okay, very important. Now remember that when you view your check number of plasmolized cells. Now of course this is normal plant cell looks like this, you know it. Okay, pardon my drawing tool. Normal plant cells appears like this. Okay, but when it is plasmolized, okay, it could appear like this. Let's see possible ways this cell can appear. Plasmolized cell. Okay, because cell membrane is angry, is detaching. cell membrane is angry, it's telling cell wall, I told you to be semi-permeable, you refuse. I told you to be, you are now fully permeable, and we have lost all our waters. Okay, so it start detaching. Now this is, less plasmolysis. Okay, yes. Anytime it appears, like if you see a cell, it's a cell membrane is detaching. Okay, know that plasmolysis is occurring. Or the cell could appear like this, depending on the concentration of the solution you place the onion tissue in. Okay, and how long you've left it there. Okay, you just look inside. If you see anything that appears that this way also, now this is it is plasmolizing here, but we'll call it more plasmolysis. So the cell membrane has started detaching. Cell wall is begging the cell membrane, don't leave me. Okay, don't leave me. We have been together for years. Cell membrane said, you don't listen to me, there's no need to be with you. So this second one shows more plasmolized. The cell is becoming more plasmolized. Okay, now the last one I'm going to draw here. So as you look into your microscope, you're going to look out for all of these, right, to show evidence of plasmolysis, right? So yeah, sorry, this is small. Now you see cell membrane here is completely detached from cell wall, right? They are separated. The divorce case is done. Okay, this is complete plasmolysis. So when you look into into the microscope, there's no plasmolysis here. But if you see something like this, okay, cell membrane is detaching, this is less plasmolysis, you can count it. All right, if you see this is more plasmolysis. Okay, this is complete plasmolysis. Any of these, you count any number of cells for each of these concentration. Okay, put their numbers here, guys. That's it. That's what you're expected to do. So you see, heading for independent variable, there must be heading for it. That's concentration of sodium chloride solution. That's concentration of S. Heading for dependent variable, number of plasma cells. Yes, that's it here. So 1 mark, right? The next mark, expected pattern. So expected pattern is that as the concentration increases, remember the number of plasmolized cells must increase. So concentration is directly proportional to number of plasmolized cells. That's the expected pattern. So W, which is water, which is 0, has lower number of plasmolized cells than 4%. Okay. All right. So that means that the lower the concentration, the lower number of plasmolized cells. Okay, 3 marks. Yeah. Using the high power lens, select 3 adjacent touching cells that show the effect of adding 4.0% sodium chloride solution. Make a large drawing of these 3 adjacent touching cells using a sharp pencil for drawing. Use one ruled line and label to identify a cell surface membrane of one cell. Remember that this is the highest, so you're going to see cells that are plasmolized, but remember they are adjacent. Okay. Okay, we can decide to draw them this way. So, let me clean it. Yeah. So pause the video and try it. But you see, in exam, you have to look inside the microscope and draw the cells. Draw the cells. Pardon my drawing tool. It's not straight. Okay, let's try it again. Yeah. Okay, this is a cell. Okay. Yeah, cell wall should be represented using double line. Okay, this is the first one. They are adjacent to each other. We can actually decide to put it this way. Okay. All right. Yeah. So there can be, right, that way. I can put another one here. Okay. So if I like, I can put one here. Okay. Just put one here. Yeah. Cell here. Okay. Each one should have a cell wall. Yeah, let's assume this is what I have. Okay, it can be like this, or if I can decide, depending on what I see, I can decide to add another cell here. Okay, all right, depending on what I see in the microscope, but you must show the cell wall. Okay, so this is also It can also be like this or the other way. Okay, so they must show plasmolyzed evidence of plasmolysis. Let's assume that this is starting to plasmolyze. Cell membrane is detaching. Let's assume that this is plasmolyzing, must see cell membrane pulling away from this relationship. Cell wall is begging her, please don't go away, or him. Okay, now this is completely detached. Okay, all right. So you see, any of these could show plasmolysis. Then you now labeled and this membrane has attached, rule label line straight. Okay, you now label it surface membrane. Identify this is cell surface membrane, this is cell membrane. Okay, cell membrane, that's the one pulling away, right? Here is attaching cell membrane, so I'm going to write it in short form. All right, okay, let me complete it. Cell membrane, cell membrane. All right, so look at it. So you can see this says lines are continuous, so that your line must be continuous. It must be thin, so you don't have broken lines. You lose 1 mark for this. These 4 marks, all these points, each of them is a mark. So if you miss any of these, you lose mark. So continuous, it must be continuous, no broken lines. It must be thin. Don't use pencils are not sharp. Okay, use sharp pencil, and at least 2 enclosed surface areas. Okay, draw only 3 cells, and each cell touching at least one of the other. So these are 3 cells. This one is touching this and this. Okay, this touching this, and this one is touching this. Okay, show plasmolysis. We have shown plasmolysis. This is plasmolysis. Okay, all right, label lines and label surface membrane. Okay, we have labeled it. 4 marks, right? That's 4 marks. So please, we are trying to, right, predict the exam. Okay, so this is what you expected. Now the next question is, use your knowledge of water potential to explain the appearance of the inner epidermal cells in 4% sodium. Remember that. Okay, pause this video and try this question. Okay, so if you put a cell in a solution that has higher water potential, lower water potential, that means the solution has a more negative water potential. Okay, 4% is quite high. So what happens is that, because they say you should use it to explain, what happens is that, why does it become plasmolized? Because water leaves the cell and moves into the solution. Why? Because the cell has more water potential compared to the solution. So water moves out by osmosis. Okay, and then plasmolysis occurs. That's what I wanted to say. See, water potential in 4% sodium chloride is lower. Okay, more negative than, so water lost from the cell surface, from cell by osmosis. Cell volume shrinks, cell surface membrane comes away. Okay, that's what you're meant to say, guys. 2 marks. Suggest how you could modify the procedure to have more confidence in your result. Now, anytime you're trying to have improvement, you look at, okay, your dependent variable. How could I have measured, counted the number of plasma cells so that have confidence in it? Okay, that is the issue of reliability. So you can count the number of plasmolized cells, count more, okay, in one solution. For example, if this is my microscopic view, after counting this, I can shift the slide, all right, and have another microscopic field of view and count another one, and then shift it using microscope, and then have another microscopic view and count it. So the number of cells, right, from this, right, microscopic field of view of the same sample, the same, all right, from the same solution, same sample, and this, I'll just add them and calculate the mean. Or I can take different samples from the same solution, count the number of plasma cells from each of the sample, calculate the mean. Do you get? All right, very important. Look at it. This could come out in the exam. Count more cells for each solution tested. Count cells in more than one sample from each solution. So you take more than one, epidermis and count the cells for each of them. Then when you are done, calculate the mean of the plasma cells from each of them. You can use photograph of image and count different piece. You can use different piece of onion tissue. Okay, use a greater range of number. All right, 2 marks. A student investigated the effect of different concentrations of sucrose solution on piece of potato tissue. The student used the result to determine the mean percentage change in length of the pieces of potato tissue. Piece of potato tissue were cut to exactly, now you see, when you're doing this experiment, there are things you must standardize. For example, the same length, the same cross-sectional area, yeah, because they could affect the number of plasma cells. Okay, each piece of potato tissue was put into a different concentration for 1 hour, so they must be left same time. After 1 hour, the length of each piece of potato tissue was measured and the percentage change in length was calculated. 5 replicates were done for each concentration. That's amazing. All right, the student then calculated the mean percentage change in length of potato tissue for each sucrose solutions. Okay, yeah, the process data are shown. All right, so what's the question? So complete the table 1.3 by calculating the mean percentage change in length of potato tissue in 0.8 mole per day sucrose solution. So if you come to this, pause the video and do it. I want to pause the video. This is 0.8. This is it. They say we should complete it. So that means we calculate the mean here. All right. But before you jump into this, guys, because there are so many of these, okay, find out, is there any anomalous value, any outlier? If you check, as concentration increases, the percentage change, right, decreases. It decreases for this, decreases for this, okay, decreases for this. All right. But when we came here, can you see? Okay, this one, see, when we came here, decreases, decreases. Okay, instead of decrease, it increased here, because this is minus 1.6 is greater than this. Okay, and then it now decreases again. So this is anomalous. We can't use it to do the calculation. The guy is the odd number, the black sheep of the group. Take him out. So you can use it to calculate our mean. So our mean will be this plus that, okay, plus this, right? That is minus 2.60 plus minus 2.50 plus minus 2.60 plus minus 2.70. All of them divided by 4. When you finish adding them, you are removing minus, yeah, so this is minus, right, 2.6, yeah, plus minus, they're all in brackets, 2.5, 2.5, okay, remember this is in bracket, but plus minus 2.6, again, this is 2, this 2 wants to become 1, this 2, what is wrong with you? Okay, plus minus 2.7. So just add up negative values, just add them up and then divide by 4. Okay, add up negative values, divide by 4. So because there are 4 of them, divide by 4. This is 4. Okay, so get a calculator, let's do it. So minus 2.6 plus minus 2.5 plus minus 2.6 again plus minus 2.7. That gives us what? 10.4 divided by 4. 10.4 divided by 4 gives you what? 10.4 divided by 4. Okay, gives us 2.6 minus 2.6. Let's give you minus 10.4. Now by the time you add everything, it will give you minus 10.4. Is that okay? Yeah. Divided by what? By 4. That gives you minus 2.6. minus 2, that's the mean. Okay, minus 2.6. Okay, oh, that's 2.6. Yeah, that's minus 2.6. Okay, let me remove this, put normal point. Okay, yeah, 2.6, that is it. So if you look at mass scheme, yeah, minus 2.6, and almost result remove. Okay, remove it. All right, one mark, just one mark. Plot a graph of the mean data in table 1.3 on the grid in fig 1.3. Use a sharp pencil for drawing graphs. Okay, so you can see that. Yeah, so I want us to plot the graph. So you just plot the graph. Remember that graph, we if you go back to the distance, you can see, all right? So just pause the video and try to plot the graph. Pause it and plot the graph. Very important. Okay? So I would like you to plot the graph, but for you to plot this graph, you must know what should be on x-axis and on y-axis. Remember, if I should extrapolate, bring this table here. Okay? So if I should bring this table here, I have something that looks like this. Okay? Yeah, sorry for this table. So I'm plotting, right? The concentration is here. Concentration is the independent variable, okay, against mean change in length, so I put like this. So remember the first one here is 0.0. Okay, yes, right. So this is 0.2, but 0.0 gave us the mean length for 0.0. This 0.2. Okay, the mean length for 0.0 is 2.7. That's plus 2.7. Okay, yeah, that's the mean length. If you check, the mean length for 0.2 is what? Is 0.3. Okay, for some people that don't know how to plot graph, or you have forgotten how to plot graph, in biology you plot a lot of graph. There are 0.4, or taking time to do this with you, right? So this is it. We have 0.6. Okay, that's 0.6. Okay, now 0.4, the value is minus 1.4 years. So if you go back to the video, you can see that I'm just writing it out here so that we can do it together. We can pause the video and start plotting the graph. Okay, 0.6 goes with minus 2.5, no, 2.2. Okay, now 0.8 is the next value, concentration. 0.8 goes with what? It goes with minus 2.6. That was what we found out in our calculation. Then the last concentration, which is 1, all right, 0.0. Okay, so that gives us minus 3. So you can see that this value runs from positive values, minus 3.0, to negative. So we have plus 0.3 and then plus 2.7. Okay, so in the so find out the middle here and draw the line if you want to plot this graph, because the x-axis has negative and positive value. Okay, so this is our concentration. Remember that independent variable is always on x-axis, dependent is always on y-axis. Okay, so independent variable here is concentration, right? Yeah, it is concentration. So because this gives you a lot of marks, so this is concentration. I'll call it C. So you have to write concentration, right, of sucrose solution, and you put the units. The unit here is percentage, and the same thing here. This is mean percentage change in length. I'll just write it in short form, and then okay, and then change. You put the percentage there. Now it's time to choose scale. The scale must always be 2 cm for all biological drawings, and of course we are choosing for concentration, which is on x-axis. We can say 2 cm, which is this is 0.2. okay, yeah, and then this is under 2 cm 0.4. you get, yes, yeah, okay, then 2 cm here 0.6, yes, okay, and then this is 0.8, no, here, okay, this thick line 0.8. So and the last one is what, 1.0, which is 1, okay. So the other one we use for y-axis, we use 1, okay. So 2 cm for 1, so this is plus 1, okay, that is 2, that is 3, this is 2, okay, this is 3. So, and of course this is minus 1, this is minus 1, negative 1, this is negative 2, okay, negative, sorry, the graph is at the edge, okay, and then negative 3 at the edge here. So I'm plotting the first one 0 and 2.7, 2.7, 0 and 2.7, this is 2, 2.7 is 3 here, yeah, okay, yeah, 2.7 and 0, so I just cross it and circle it. That's the first plot. The second plot, 0.2 and 0.3, 0.2 and 0.3 will be here, plus, okay, 1, 2, 3, okay, yes. So remember that each box for x-axis is 0.02, each box on the y-axis is 0.1, because 10 boxes gives us 1, so all right, 1 should be 1 over 10. So 0.4 and minus 1.4, 0.4 and minus 1.4, that should be 1, 2, 3, 4, okay, here, all right, yeah, can you see? Then 0.6 and minus 2.2, this 0.6 minus 2.2 should be here on 0.6, okay. So I hope you're plotting. Then 0.8 minus 2.6, 0.8 minus 2.6, 2.6 should be somewhere here, right? And then 0. That's 1, and yeah, and 3. So yeah, okay. So once you are plotted, you have to join all the values. That's what we do in biology. Join this to this. All the points must be joined. Sorry. Connect this to this. There's, right. Don't miss anyone. Connect this to this. Connect that to that. So connect this to this. Right. So this is my graph. Now, if you check, they always ask you, right, where there's no change in mean, okay, length. That is where the water potential of the potato is equal to water potential of the sucrose. That is where there's no change in length. Remember that y-axis is mean, all right, percentage change in length. Okay, where is it 0? That's where it cuts here. And where it cuts here is this is 0. This is 0.2, 0.22, 0.23, 0. No, each one is 0.02. So 0.2 is 0.2. Edit. Where is it? Yes. 0.22, 0.24, 0.26, I guess. Yeah, 0.26. Okay, 0.26. Yeah, is here. Um, yeah, see, we're taking time to explain this, guys. Okay, so this is it. So that there's no the change there is there's no change in length. Okay, so if you look at the math scheme, all right, see what math scheme says. Yeah, this is about 4 marks. If you're going to plot graph, now I want to say that most of the answers in practical is locked in follow-up questions like plotting graph and other questions. Most of your answers will come, so you have to pay attention to all of this. Okay, analysis. So you can see quickly. X-axis should be concentration because it's independent variable. It puts the unit, which is mole per dm cube. Y-axis mean percentage change in length. That is it. You have to label it, and then percentage should be there. Scale 0.2, so the unit 0.2 is always 2 cm. 2 cm, 1%, 2 cm. Correct plotting, 1 mark. Joining, 1 mark. That's 4 marks. Okay. All right. Fig 1.4 is a calibration curve of sucrose constraint against water potential. So they say use the graph in Fig 1.3 and Fig 1.4 to determine the water potential of the cell in potato tissue. Show on the graph how you determined it. Okay. Remember, I told you that we have already determined the concentration where there's no change in length, because that is where the water potential of the potato tissue is the same as that of the that of the um, that of the solution. Okay, so what you just need to do is just, and we found it to be 0.26. So here, remember that here um, you have to realize that you have, for you to operate, you have to know the value of one box. From here to here is 0.2. That's 5 boxes gives us 0.2. Okay, one box will be 0.2 divided by 4. So divided by 5, because 5 boxes is 0.2. One box is 0.2 by 5, which is 0.04. Okay, so one box is 0.04. Okay, 0.2 by 5. So you have to find out that before you continue. 0.04. So we're looking for 0.26. So if this is 0.2, that's 0.4. 0.26 will be between 0.4 and 0.8. Okay. So you come here, somewhere here, you show it. Okay. You trace it here. Okay. This is in between the boxes. When you get to this point, see this point, you now trace it. Okay, this is that concentration. Okay, remember you have to first of all determine the concentration using the other graph you plotted. All right, so you can see now from here to here is 5. So 5 boxes gives us 500 minus 5. Okay, that's minus 100. Okay, this is going to be minus 700. Okay, it's minus 600 minus 700. All right. Yes. It's no. It's gonna be. This is minus 500. Each box will be 500 divided by 500. Yeah. So that's 600, 700. So minus 700. Okay. Minus 700. So that is this answer. Minus 700 kilopascal. That is the water potential of the potato. That is the water potential where there's no change in length. Okay. See. Let's look at it. So correct sucrose reading from Fig 1.3, the one plotted, at which there's 0% in length. Okay, so that was our 2.6. We now came here, use the 2.6 here to extrapolate. Right, the 2.6, there was 0% change in length. We brought it as concentration and then trace it to water potential. Okay, so 3 marks, guys. All right, quickly let's look at the second question. Time is fast spent, but let's look at it. Manufacturers of fruit juice need to know the concentration of ascorbic acid, vitamin C in fruit. The fruit is picked um, when juice contains the highest concentration of ascorbic acid. Concentration of ascorbic acid can be estimated in a fruit juice extracted by carrying out a test using starch solution, okay, and iodine. So remember, as you are reading this, find out the independent variable. What are we changing? What are we measuring? Iodine solution will be added 1 drop at a time using a syringe. To practice releasing drop from a syringe, fill a syringe with 1 cm cube still water. Hold the syringe over an empty test tube as shown in figure and push the plunger while you release. So you have to practice, repeat this until you can release it. So practice this, okay. Now you are provided with materials shown in table 1.1. Like I told you, you must look at on the bench and look at what is there. There's no hazard here. So A is ascorbic acid, distilled water, iodine. If any solution comes in contact with your skin, wash off immediately under cold water. It is recommended that you wear suitable eye protection. You will now carry out a test on A and W to practice the method and find the volume of iodine solution that needs to be added for the endpoint to be reached. Okay, so iodine reacts to produce blue black, but here is blue remains after, that's endpoint, after 10 seconds. All right, they said put 1 cm cube of S into a test tube, put 5 cm cube of A into the 10 test tube, shake the test tube gently to mix the content, fill a 1.0 cm cube syringe with exactly 1.0 cm cube of iodine, wipe off any iodine from the outside of the syringe with a paper towel, put 1 drop of iodine as shown in figure 1.1 the mixture into the mixture of S and A in the test tube. Mix gently and observe any color change. Repeat steps 9 and 10 until a blue color appears. You may need to refill the syringe with iodine as in, okay, 7. When the blue color appears, shake the test tube for 10 seconds and see if the endpoint has been reached. So if the blue color disappears, then repeat 9 to step 9 to 12 until the mixture stays blue for at least 10 seconds. Record AI, the volume. So you see, what you're recording is volume. That's what I mentioned. That's your independent variable. The volume of iodine solution added, right? Repeat steps 4 to step 14 using W and this. So you record the volume. That's what we're measuring. So this, you are checking the percentage of ascorbic acid in water. Okay, they mentioned checking 2 of them, but the volume of iodine used to reach endpoint will be used to determine the concentration. All right. Record volume of iodine added to sample. So whatever you did in the practical, you record it as you follow the instruction. You will need to prepare known concentration of ascorbic acid using proportional dilution. Carry out, right? We have done this at the beginning. So making simple proportional dilution of 0.1% by reducing concentration by 0.02. So that this is going to be the interval. You will need to prepare 20 cm cube of each concentration. So this is our final volume. All right. So this is your final volume. So that means that you're going to need to prepare it. Okay. So if you have the table, you know that the first one here is 0.1. I'm just gonna, all right, can pause the video and try it, but normally the table is going to be shown to us, right? So this is concentration. You put the unit here, okay, to be shown to us. This is volume of stock, right? Yeah, but before we start, this is 0.1. Let's not waste time here. So the next one is 0.1 minus 0.02. That will be 0.08. Okay, these are the concentration. So minus 0.02. Why are we doing that? They say the concentration in between is 0.02. So keep minusing. All right, 0.06. Okay, this is 0. This is 0. 0. All right, the next one is 0.0. That's 0.06 minus 0.02 will give you 0.04. You know that. Okay, and then 0.02. Okay, yeah, so that's it. So you got the volume for the other one. So see, when we're doing the proportional dilution here. Okay, so guys, all right, so you know you're gonna have to produce each cell on this table. Okay, so yeah, gonna have to produce 3 more or 4 dilutions. Okay, the ones we have written down. I want to pause the video and write out those dilutions and work them out. 4 of them. Okay, and I think this is it. Yeah, so don't forget um sorry for the table. All right, now of course this is going to be 0.08, right? Okay, yes, so this is going to be 0.06. Okay, that's 0.04. Okay, yes, and that's 0.02. 0.02. Okay, so you need to find the volume of the stock you need. That's the V1 for each of them. Okay, so if we're moving from 0.01 to 0.08, we're using this to produce this. Okay, yeah, remember that we're looking for V1. Okay, you're moving from here to this, so the volume that you're gonna need to add here, sorry, is my V1. V1, you know the formula, is equal to what? We have done this at the beginning. C2 is 0.08, right? V2 is the final volume, which is 20. C1 is a stock, which is 0.04. Okay, that's C2 here, C1. So our V1 here is C2 0.8. So 0.8, okay, 0.08, sorry, that's our final concentration, times 20. Yeah, 20 is the V2 all over C1, which is 0.1. So what do you have? So bring your calculator. So you're going to have 0.08 times 20. All right, that gives you 1.6 divided by 0.1. Okay, 1.6 by 0.1. That's 16. So I get it. 16 here. So we're going to put water. What I'm going to put here is 4. Volume of water before. So just keep removing 4. Remove 4 from 16, it will give you 12. Add 4 to 4, it will give you 8. So it's easy to track this. Remove 4 from 12, it will give you 8. Add 4 to 12, it will give you 12. 4 to 8 will give you 12. The last one, remove 4, this give you 4, and it gives you 16. See, we have done this table. 2 marks. Okay? Alright. See? All the volumes, 2 marks. So prepare the concentration of ascorbic acid. We have done that. Repeat step of the concentration table 1 point. Record your result. Repeat, all right, for each of the concentration. So they say we should record our result. Remember that we have not carried out this practical, but you know what to do. First of all, here you must know, draw an enclosed table, and your independent variable here, what are we changing? Concentration. So you must know what you are changing and what you're measuring. What are we measuring? The volume of iodine used. So our table should be like this. This is concentration, okay? Concentration of A, or whatever you call it. Concentration, I think is concentration of A. And then you put the unit here, percentage. This is volume of iodine used in cm cube. Okay, yeah, and then you now write all those percentage here and the volume for each of them. So 4, no, the 0 0.1, 0 0.08, 0 0.04, 0 0.02, and 0. So all those concentration will be here, and their volumes should be here. Okay. All right. So you see. So heading this percentage concentration of ascorbic acid, that's our independent variable. The second heading should be volume of iodine used, then volume of 5 concentrations, and then records volume. Okay. It's not hard, guys. 4 marks. You will need to estimate concentration of ascorbic acid in X and Y. So if you're doing this practically, you just do for X and Y and find the volume, the same steps. Okay, the volume used. All right. Now, complete table 1.2 show the table. So you just by the time you carry out, there's what the same steps on X and Y. Okay. So the volume will give you an idea from your table which concentration they are close to. Okay, if the volume is close to that of 0.1, you come here and take 0.1. If it is close to 0. Maybe 0.06, you come and take it for each of them. Okay, so based on the results of this, that determines the percentage you estimated, and then you mark it off here. Okay, so concentration table written on. So you have to compare it with X and Y, and then be able to determine that. All right. Identify the significant source of error here in this experiment investigation. You know that you are dropping. If you are dropping, it's possible that the drops can touch the side of test tubes. Okay, the size of the drop is not the same. Okay, and it's difficult to judge color change. Look at it, not hard. Look at them. Drop sticks to the side of the table, difficult to judge. Now, drop size changing, iodine evaporates. Okay, these are the. So how do we correct it? It was asked you how to correct it. How do you correct it? So pause the video and check it. So how are you going to improve? Through improvement, of course, you can use smaller test tubes so it doesn't stick. Okay. Now for color measurement, you can use colorimeter. Look at it here. Okay. Or of course, we use the wider range. If you use proportional dilution, wider range, you can use narrow range of concentrations. Of course, the pipettes, any of these can be changed because they give us better. Use graduated pipettes range, they give us better value. Colorimeter can also be used instead of using the eyes to compare colors. Put drops in nearer. Okay, these are the things. Plot a graph, read them. Okay, use a wider or lighter reporting tube. Okay, so these are the things that actually could improve the experiment. A student carried out further investigation on ascorbic acid tests on its reaction on amylase starch. Maltose is a product of the hydrolysis of starch. The different concentration of ascorbic acid were added to standardized mixtures of amylase and starch. The student measured the mass of maltose produced. So look at it. This is concentration. This is mass produced. Okay. So first of all, check the trend. Consider as this is increasing. Okay. What is happening to this? This is decreasing. So the now said the results are shown in table 1.4. So you can see that. Plot a graph of this data. So you're going to plot this graph. Make sure that you can try it here. So what's the independent variable percentage? It should be on x-axis. Independent should be on x-axis. Write percentage concentration, and then you write the unit. So on y-axis, mass of maltose. Okay, write the unit 2. Right. So you choose normal scale here. 1, of course, 2 cm for 0.02. This is going to use like 20 or 50. 50 is okay. Okay, 20 is fine. From here to 20, 40, 60, 80, 100. Yes, for this. And then you plot. So after plotting, it should give you something that goes down like this because they have a negative. Okay, the graph should go like this. So if they now ask you to determine maybe a particular percentage, if they say you should determine 0.0, all right, maybe 0.5, which 0.5% of ascorbic acid, you just come whatever it is here, somewhere here, right? Trace it to the graph. So they're asking you what percentage will it give you more to trace it to, and then trace it, and then read off the value. That's it. Okay, that's it. So this is for plotting on the graph. What the things you need? 2 marks for plotting it. So use the graph. That's what I just did now. Just read off the graph. Okay, read it off. Yeah. So just explanation for the result between. Now you can see that as it's increasing, as the concentration increases, what happens is that the percentage of maltose produced decreases. Why? All right. Remember that either that the ascorbic acid is increasing the concentration, so solution becomes more acidic, so the enzyme becomes denatured because pH can break hydrogen bond and ionic bond. So the active site becomes distorted, less substrate binding to the active site, right? Fewer ES complex form. Or you can say that this ascorbic acid is inhibiting the amylase enzyme, right? It's acting as either competitive or non-competitive, binding to the act, changing the shape of the amylase enzyme so that it doesn't bind to starch unless maltose is formed. So any of these, okay? Okay, that's explanation of the reason why, as we increase the concentration of ascorbic acid, what is happening is that the amount of maltose formed is decreasing. Okay. So this is where we stop today. Thank you so much. Please make sure you go over the video series 1 and series 2 and get ready for exams. Okay. Bye. This is Shedro. See you next episode.